Okay, Mike, good morning.
Yes.
Good morning.
Yes, I can hear you.
Yes, we hear you perfectly. And we saw you also. Look,
Let me share.
you are
I will share-
you are not seeing the room, but here are 40, more than 40, 45 people expecting your talk very anxiously. And also people from, as you probably know, from different parts of the world, like Japan, Russia, Italy, and France. So we really expect. I want to introduce you just a few. Dr. Mike Campbell is presently the director of the Laboratory for Laser Energetic at the University of Rochester, which hosts the second laser more energetic, more powerful in US, and the third in the world is the laser Omega and Omega EP. Omega, which is a nanosecond, and Omega EP, which is a picosecond lasers. So in addition to that, he was certainly one of the key persons when the National Ignition Facility started and make the good programs to arrive to the ignition in US. So the personality of Mike Campbell is unquestionable. Is a key person for us. In the other alternative that talked Carlos Alejandre, which is inertial confinement fusion for energy. So, Mike, after this introduction, please go ahead, and thank you very much because of the organization to be here at 4 o'clock, 4:30 in the morning of Rochester time. So, my friends, 4:30 in the morning, and he's here teaching us about inertial confinement fusion. Thank you very much.
Okay, first it is early here in Rochester, New York. I wish I was there in your wonderful country, but it is a time of budgets with government, and so I must spend my time here in Rochester. I'll be going to Washington later today. So I know everyone understands, but I will do my best to talk about ICF, where we are today, energy, obviously, and what some interesting spin-offs that already occurred. So thank you, Manolo, for inviting me and the rest who were part of this, and let me get started. Okay? All right, motivation. So I will first give a little bit of motivation about fusion. Many of you probably have aware of this, but it's always good to remind people why we need carbon-free energy. So first of all, energy powers the planet in every way we know, from transportation to electricity to industrial production, movement of goods. All right, so we know how important energy is. It's also, how do we quantify how much we need? So many years ago, people at Livermore elsewhere tried to quantify the needs of people for energy. How much do we need in the future? And they developed a thing called the Human Development Index. What it is, it combines life expectancy, literacy, how educated the population is, the GDP per person, and finds that, of course, it correlates with annual electricity use per person. And you see that the developed countries that we're all familiar with are typically 5 to 10,000 kilowatt hours per year. And you see that developing countries, which are rapidly developing, like China, to a lesser extent India, of course, are much below that. And so as we project what we need over this century, which is a very important century for the planet and for humanity, we clearly need more energy. But when people become wealthy, they also learn they want increased mobility. I mean, I use the United States as an example, but also in developing countries. And you see that on the right-hand side, you see that as people get more wealthy, they tend to buy cars, and they will buy electric cars, of course, in the future. And then public transportation and other things decline. So energy needs are going to continue to increase as the world gets more wealthy. Next few graphs will show. So yes, okay. So as I explained, the quality of Human Development Index, which is the quality of life, if you will, correlates with electrical use per person. And you see that most of the world is down here, and we need a lot more energy than we have now. Of course, hydrocarbons are not the answer. We're about 400 parts per million, CO2 in the atmosphere. You see what Greenland looks like. You see the tar sands over in Canada, which are horrible. You see, being in the US, we fought many wars. This is from GA, a Predator. And here's something interesting, of course, that's happened this past year. The average temperature of Seattle in June is about a little over 70 degrees Fahrenheit. It's been 2 days this year when it's been over 108 degrees Fahrenheit, 42 degrees centigrade, and 40 degrees centigrade. So all my friends in the Northwest are, let's just say, in shock over how the planet climate is changing. And of course, we know that to be a case. So there is no silver bullet for the future energy. We need lots of things. And we need, obviously, it must be carbon free. The question is, how much do we need? Right now, the world generates around 3 terawatts of electricity, which is about a third of use of power. We'll need more than double that probably by the end of the century. So also, it's a good discussion now about how many people will be here as the world gets wealthier, as women go into the workforce, education and the like. How many children are produced are going down? Most of the industrial countries have less than 2.1 children per woman, which of course means over time the population will decline. So it's very interesting to see how many people we will have in the world in the end of the century. There is increasing debate about that. But of course, for fuel, for energy, it must be carbon free. We all know that. It must be abundant, geographically diverse. There's a lot more things than electricity produced, right? You must process heat for industry, hydrogen and biofuels for transportation, and water production. I live in California, and even though we have 1,000 miles of coastline, California has water problems all the time. California spends more money moving water around than it does anything else. Of course, we have to become increasingly efficient, but what happens when we become more efficient, people buy more cars. It has to be able to, when you need peak electricity, you get it. When you don't need it, you actually can reduce the amount of production you need. So it's called load following. We all must conserve. You must have distributed energy sources, but you also must have central. And I want to talk about that. That's where fusion fits in. And by 2050, the UN estimates that over 60% of the world's population will live in cities. Now, this is pre-COVID, but I think as the world gets back to normal, this will still become true. And when you live, and I live in San Diego, even though I work in Rochester, and I pay more money for transmission of electricity than I do for generation. This problem not only is a money problem, but many of the wildfires in California are caused by arcing of transmission lines. In 2008, my house almost burnt down because of arcing of transmission lines east of where I live, taking power in. So we need to be able to produce power close by urban centers, in addition to distributed sources like wind and solar, which generally are not where people live. All right, so we need to be able to keep that in mind. It's a motivation for fusion that is generally not always talked about. So of course, as everyone knows, I also draw cartoons. And of course, there's Edward Teller. And so again, for central power production, you want to make sure the fuel is dispersed around the globe so everyone has access to it. It's got to be acceptable environmentally. It has to be passively safe. Of course, nuclear fission, has had its issues. Here's Fukushima in a developed country. Here's Chernobyl 35 years later. Obviously, the public has got to be very comfortable that there can be no accidents like this. And of course, that's something which fusion can do. So fusion, of course, is the answer. I do believe there will be expansion of advanced nuclear fission that is passively safe. That can be done with advanced reactors. And we will see that as part of the mix too in the future. But of course, it must be able to produce all of these other forms of energy, which we need in the future and we need today. Let's talk about fusion fundamentals. All right, so interesting to know that both fusion and fission were discovered in the same decade in the 1930s. Fission in a German laboratory of that time era. And of course, a neutron comes into a heavy element, uranium or other fissionable material, It causes unstable nucleus, it breaks apart, of course, produces more neutrons and fission products, which cause problems. And there's Albert Einstein there looking at what this E equals mc squared has done. And of course, it's a room temperature process since the neutron is uncharged. And interesting to note, within a few years, nuclear reactors were not only constructed, they were operating. In the Manhattan Project in the United States, there were reactors in 1944, just a few years after its discovery. And of course, today, many more. Fusion, of course, is different. It requires the merging of two light nuclei, and the electrostatic repulsion force is very high, of course, inversely proportional to the square of the distance. And to be able to have enough energy to overcome that electrostatic barrier, particles must be moving at very high speeds, which means very high temperatures. So DT fusion, of course, combines the two heavy isotopes of hydrogen, deuterium, which is naturally occurring, and tritium, which must be produced to form a compound nucleus that then breaks apart, makes helium and a neutron, releasing 17.6 MeV per reaction, which is about 2% of the mass of a proton. Of course, it was identified also in the 30s, but not in a laboratory, but trying to understand why the sun could burn as long as it did. By the late 19th century, geologists knew that the Earth was billions of years old, and how could the sun produce energy just from gravitational collapse was not enough. And of course, Eddington and Hans Bethe in the 30s came up with the process within a sun of fusion. And it's been ongoing research since the 1950s. We still don't have it, but we will sometime this century. Next view graph. As you know, many research in the United States in particular is done with national security. And ICF in the US has a lot of that focus. So here's an example of what has happened. Here's Admiral Rickover. He wanted a nuclear-powered submarine. Today in the US, we have 94 reactors, 58 plants producing about 20% of the electricity in the US. 55% of the carbon-free electricity is generated by nuclear. Of course, national security has done much more than just that. In the end of July of 1945, towards the end of the Second World War, Vannevar Bush, who was President Roosevelt's science advisor, came up with a report why science is so important for the future. And he wrote this book, or actually a report. It's called The Endless Frontier. A lot of discussion now in the US Congress about reestablishing this vision. And of course, what that did, it generated high performance computing. How could we live without computing today? It was a motivator for that. For space, we all know how important space is, not just for putting astronauts there, but I don't have maps anymore. We can see weather predictions. We communicate like we're doing today. And of course, things like radar. So Fusion ICF also will benefit from this national security perspective. Now, and why? This is a nice view graph that my friend Dennis White of MIT gave to me about the promise of fusion. This is DT, of course. There are other fusion fuels, but they are more difficult. DT will be almost certainly the first one that will be demonstrated commercially. So, of course, here's a super tanker. It carries about 320 million liters of oil. If you put this in a big bathtub, it would displace about 24,000 liters of water. If I take 40, in that water, there's about 40 liters of deuterium. If I also have to breed tritium because it's not naturally occurring, I then can fuse it like the sun does, although it's a different process than the sun, but it's still fusion. But that 40 liters of deuterium and tritium will produce as much energy as in this tanker's oil, and of course not emit 200,000 tons of CO2 in the process. So fusion is eventually going to take us there. And now let's talk about where we are. Now, of course, it works. The sun, we look at the sun every day and all the stars. It works in nuclear weapons, which we want to do. There's a wonderful movie that was done in the early 1950s. It's called Forbidden Planet. It actually is the first movie with moose, robots, Robbie the robot, and it has 8,000 cubic miles of fusion reactors powering the planet. Of course, we don't have that yet, but where are we going to get? How close are we? So, of course, the challenge for fusion is just not getting the temperature. It's controlling this plasma for the time duration so that net energy can be released. So one way of looking at what you need is what's called the generalized Lawson criteria. We put it in context of pressure, the plasma pressure, which is density and temperature. and the time and the energy confinement time. A good number to remain is that to get net energy release, you need some 10 atmosphere seconds of this product. So the goal of the fusion research, and whether it's magnetic or inertial, is to be able to get a product of the pressure times the time, which is about 10 atmosphere seconds, an easy number to remember. Now, of course, the magnetic fusion, and we have this big project in Bordeaux, France, this international project to make a magnetic fusion with a tokamak. The plasma density to about 10 to the 14th particles per second, and basically an atmosphere, about 10 atmospheres. So the energy confinement time is about a second. And to the densities, again, 10 to the 14th, about density of atmospheric density. ICF, of course, takes the other extreme. There is no confining magnetic fields. It is just the inertia of matter, its inability to instantaneously move when forces are applied. And so the plasma is confined by its inertia, which means we get it to extreme densities, a million times higher than atmospheric density. And of course, the confinement time is the inertia time, which is only about a tenth of a nanosecond. So ICF creates matter at these extreme conditions. And that's what we'll be talking about the rest of the talk. All right, let's talk about ICF. All right, let's talk about what an ICF power plant would look like. So first of all, what are the features? You look over in the left-hand side, you see that a pulse system operating from of a hertz to 10 hertz. The driver energies, and you'll hear about this from later on from Inovan in this talk, of course, be somewhere from a megajoule to maybe up to 20 megajoules. More energy means more mass imploded, which it makes it easier. Peak power is 500 terawatts, more peak power than the planet. An average power of 3 to 10 megawatts given that rep rate. And to give you a sense, the targets will be somewhere 10,000 to a million a day in this system. That's what we have to be able to do in an IFE plant. Now, of course, I'll show what that is in a second. What are the advantages? Let's talk about there's our reaction chamber. There's our target factory generating those thousands of targets a day. Here's our driver showing a laser here. Here comes, obviously the laser has to couple its energy into the reaction vessel. Tap a target down. We shoot the laser implodes. I'll go through the physics in a minute. Energy is released. It's captured in the first wall. Mike Tobin will tell you more about that. We make electricity, hydrogen, or other things. And we breed tritium in the process. So of this way of doing things. First of all, you see the separability of the components. They're highly modular. That allows you to develop things in an attractive way. I don't have to develop the laser all at once. I can develop components of the laser. I can do things separately and optimize them separately. I can actually develop, demonstrate a plant that's non-nuclear by showing all these components, but not having a nuclear process in there. And I can then develop with single shot facilities, the nuclear processes and the fusion physics. And that's what we're doing now. Of course, fueling and ash removal is straightforward in a pulse system. You inject mass into every time you shoot. And of course, the ash goes away. There's a lot of technology and science spin-offs, which I'll talk about. There's lots of ways of doing it with the same driver, a lot of different concepts. And of course, there's multiple sponsors. A lot of people are interested in some of this technology. For example, in solid state lasers, laser diodes. So there's a lot of things that advantage this. And one of these days, this will be how we'll make fusion energy, I believe. But this is how it works. Now, there's another advantage, as I mentioned, there are multiple ways of doing this. There's what's called indirect drive. That's done at Livermore. Los Alamos participates. Facilities, this is, again, focused on the US. NIF is a major facility for this, and also Omega does experiments for indirect drive. Here you convert the light directly into X-rays. The X-rays then illuminate a capsule, and I'll explain the process in a minute. Laser direct drive, of course, we shine the laser beam directly on the fusion device, the capsule. That's being done at Rochester. We have lots of participants, Naval Research Lab, Livermore, Los Alamos, many others involved. Again, US focus. The facility is Omega, but we're also doing experiments on NIF, which is very important, and the Nike, which is a KRF laser at NRL. There's also a pulse power approach, and where a very high current is used to implode targets. I won't be talking much about that, but that's something which is being done at Sandia with Livermore, Los Alamos, and Rochester participation. The main facility is the Pulse Power Machine Z. which is about an 80 terawatt machine at Sandia. And experiments related to this, even though it's not pulse powered, they're concepts which use lasers as part of the target concept. They're done at Omega and Nif. And of course, there's lots of innovative variations within each approach. So what are the advantages and challenges? It's always, the great advantage of having many things, but you have to look at what is good and what is bad in each one. So an indirect drive, what are the advantages? First, I can make X-rays lots of ways. I can make it with lasers, I can make it with pulse power, I can make it with ions. It's got favorable hydrodynamics, which I won't go into all the details, but the deposition of the X-rays into the target are advantageous. It makes hydrodynamic instabilities less challenging, although they're still challenging. And it doesn't have some of the noise sources, what I'll talk about when a laser shines directly on it. The whole room smooths out a lot of the non-uniformities of the laser, not all of them, but it smooths out the high spatial frequency ones. But one of the challenges, of course, is lower gain, because you must convert the light into X-rays, and then you must have a geometric loss between the capsules, not the size of the hole room, as you saw in the last view graph. And that reduces the energy to the capsule. And it's very straightforward to show that the pressure that you need in ICF is inversely proportional to the square root of the energy that you can put into the target. So less energy means I need higher pressures. That means I need more convergence and more challenging implosions. The hole rooms are big and they're complicated, and laser plasma instabilities, which I'll talk about, are always a concern. There's you shine a light in a high Z hole room. It also makes high frequency photon radiation, which can preheat the target and prevent it from compressing. And of course, there's reduced diagnostic access because the whole room surrounds a capsule. In direct drive, what are the advantages? First of all, more energy coupling. That means the pressures are lower. That means the convergence that you need are lower to get ignition. You can run it less demanding implosions overall. Higher gain, of course, because you don't have that loss mechanism, if you will, in converting light into X-rays. Lots of innovative approaches, shock ignition, fast ignition. A lot of that's being done in Europe and Japan, and they're very, very exciting to see the progress in that, which I will only mention, I won't talk about in the rest of my talk. A lot of diagnostic access. Implosions are three-dimensional. You like to take measurements in 3D. Of course, the challenges are hydrodynamic instabilities. In all ICF concepts, that's a problem, but it's even more stressing in laser-driven ablation because that's done by electrons. Electrons have shorter mean-free paths than photons, and it causes more demanding hydrodynamic stability. Lasers are not perfect. They have spatial non-uniformities. I'll talk about that later. And those spatial non-uniformities can imprint themselves on the capsule and act as noise sources for hydrodynamic instabilities. Again, I mentioned the hydrodynamic instabilities are not as, the electron-driven ablation is not as effective in reducing the instability challenges with Raleigh-Taylor. We have thin shells because less ablation. And of course, laser plasma instabilities because the light directly impacts the capsule and is close by. Pulse power, the advantage of that, of course, is large energy coupled to the fuel. There's generally not laser plasma reactions because it's done with pulse power, and high driver efficiency. But the challenge is, of course, light can propagate in the vacuum. Pulse power, I must need an electrical connection from my driver to the target. I won't be talking about that the rest of the talk, but there are some interesting ideas to get around that, but it is a clear challenge. All right, so how does this work? How does ICF work? So up in the right left here, we see a target and we see a laser pulse. You see it's structured in time. That laser pulse or X-ray pulse, which again follows a sort of similar temporal profile, irradiates a capsule. A capsule is just think of it as a spherical rocket. It's got rocket fuel, the ablator. The rocket fuel, the payload is DT. We freeze it to get the highest density as possible to start with, about 0.2 of a gram per cc. The radiation ablates, adds energy to the ablator, it blows off. The reaction force implodes the target and compresses it to these extreme conditions. And this is what it looks like when it's compressed. This time history is done for this reason. You have here's a radius of the target, and you see it's got essentially two regions. It's got a central region, which is called the hot spot, and that's where fusion is started, where it ignites, and the rest of the fuel surrounds it and basically confines it, but also provides the fuel for high gain. So what in an ideal situation, fusion starts in the middle, and a thermonuclear burn wave propagates out and will burn up to, depending on, if you will, the areal density of this fuel here, up to 30% of the fuel will undergo fusion. To give you a sense how much mass is involved, so the energy for fusion that you produce is the energy per gram, if you will, of DT fusion, times the burn-up fraction, how much of the fuels burn up, and then, of course, the mass of the DT. The fusion energy for DT is about 400 megajoules per milligram, a lot of energy release. Burn-up fraction goes as the areal density in a function of temperature, which is about 6 in conditions for ICF. And for equimolar DT, for getting 100 megajoule yield, I need about 3/4 of a milligram of DT. But to start this ignition, to light the match, requires a temperature of around 5 kilovolts to overcome all the losses, and an areal density of around 300 milligrams. And I'll talk about why you need that in a second. Next view graph. So here's the details of this implosion. So over on the left, you see the energy into this implosion goes as the absorbed energy of the target, whether it's X-rays or optical light, times the rocket efficiency, because again, this is a spherical rocket and it's a hot rocket. And so the efficiency of which that energy is converted into kinetic energy is called the rocket efficiency. That product is 1/2 of the shell and the velocity of the implosion velocity. Half that energy basically goes, because there's time history, to heating this hot spot, the 5 to 7 kilovolts. And this is a specific energy per gram. To do that, you see how much energy it requires to get things up to a few kilovolts. This is per mass, and so of course you want to do that with only a small part of the fuel. The dense fuel here it's compressed to very high densities, up to 1,000 grams per cubic centimeter, very high density. And again, ignition starts here, propagates into the dense shell. And this dense shell is both the fuel and the confinement for it. It tamps it and increases the confinement time. And you want to do this with the minimum amount of energy. Typically, over 90% of the fuel mass is in this shell. And you want to make sure that you don't use a lot of energy to do that. So you want to compress this and keep it as cold as you possibly can during the implosion. And this is what happens if you are able to do this with minimum energy, which is when basically the gas, if you will, the plasma is a Fermi degenerate material. Just the pressure, if you will, is related to the degeneracy of the electrons. These fermions don't like to be in the same phase space. Alpha is a product of saying how bad you do. You'd like to have this be 1, but most of the time it's going to be 3 to 5. And the smaller this is, the more demanding it gets it. Here again is a profile. You see the ion temperature, which is 5 to 6 kilovolts as a function of radius. You see the dense shell. This is almost isobaric. The pressure in the shell, there's enough time for many sound transit times, so it's close to be isobaric at pressures depending on how much energy you can put in this entire system. And so to give you I'll talk about that in a minute, but typical pressures must be over 100 gigabars and higher depending on how much energy you're able to put into the implosion. So ignition is essential. Here's Albert again telling us about that. So here's our deuteron and triton. Again, when they fuse, they make the neutron, carries away 14 MeV of energy. The alpha carries around 3.5 MeV. The alpha, of course, is charged. If the plasma is sufficiently dense, it stops in the plasma, heats up the electrons, then heat up the ion, increases the fusion temperature, the temperature and more fusion takes place. So ignition is sort of a thermonuclear instability where fusion runs away until it's basically quenched by the hydrodynamic expansion of the target. The ignition condition is the alpha power, which is the power in this particle here, which is about 1/5 of the total fusion energy, must be greater than the power losses, which are radiation, conduction, and hydrodynamic expansion. So what we've come up with is a way of measuring progress. And so what you do is you take eventually the pressure, this general loss in parameter, which is the pressure times time, and divide it into what's required for ignition. We call that chi. That is the implosion parameter. I'm going to go back here. That we measure. So when chi is 1, you have reached the conditions where ignition would take place. Now this happens when there's no alpha heating, which I'll explain in a minute. Now there are ways of measuring where you are with experiments. You like not only to use computation, you like to actually have an experiment parameters that you can measure to tell you how close you are. And that's the areal density, this rho r, and it's also the yield divided by the mass of the target in stagnation. So this parameter here is that we use in ENERGÍA and Nif experiments to tell us how close we are to igniting a plasma. And then if you want to scale this from ENERGÍA to Nif, you scale this pressure times time. The pressure is invariant, the pressure is the same, but of course the confinement time is going to be related to the size of the target. the size of the target is related to the cube root of the energy or absorbed energy that you have. So if I get this chi at omega, I multiply it down here by the ratio of the absorbed energies actually. That's about 4 or 5, and that's what it would be if we had an omega the size of Nif. So that's how we measure progress. Now, of course, one of the other interesting things about DT fusion is the alpha, when you have sufficiently high performing targets, the alpha begins to deposit their energy and you now have more fusion taking place. The last number I gave you was the value without having ignition or without having alpha deposition. So the yield that you get actually is not just the yield you get from having, if the alphas were neutrinos, but there's an amplification factor which is related to the alpha, how much energy the alphas stop in the plasma. And now we call that the alpha amplification. To give you a sense, a burning plasma is when the alpha amplification is around 5. That means the alpha deposition dominates the hydrodynamic work. And then ignition occurs, you see over plot here, this is the yield versus if the alpha particles were neutrinos, how it goes up. When you have alpha, this chi of 1, you have ignition, which is about an alpha amplification of somewhere between 20 and 30. So this is a way of measuring your progress, is how well you do with chi, and then how much alpha amplification you have. So let me talk about Nif first before I go to direct drive. So here's the energy flow in X-ray driven target today, which of course is not one as you do for energy. So here's a capacitor bank of Nif. It's about 400 megajoules stored. That energy energizes flash lamps. Those flash lamps energize neodymium in a glass host. We then frequency convert that to 3 omega, which I'll talk about later. We have a pulse shape that looks like this. So it's about 2 megajoules. So this 400 megajoules of electrical energy is 2 megajoules of optical energy. We then inject this into a hole room. And that hole room is heated up to about 300 volts. Max Planck would have been very interested to see the black body radiation from that. That hole room then, those X-rays irradiate a capsule. About 200 kilojoules to 300 kilojoules go into the capsule. And about 5 to 7% of that energy goes into the implosion. So right here, you see the implosion here. So you see how inefficient ICF is and why we need high gain out of this small fusion device. And ongoing research at NIF is to increase the energy coupling from the hole room into the capsule, from the sort of 10% to maybe 20 to 30%, which is underway right now, and good progress is being made. So this is just a summary of what NIF has done before I go to direct drive. This is a fusion yield as a function of time. And you see NIF has recently achieved a fusion energies of around 170 kilojoules total. And that's a gain of around almost 10% to laser energy. But you see most of this, about 5 times of the energy produced in the hydrodynamic down, let's see. The blue here is the fusion energy that would be produced only by the energy of the implosion. The red here is the energy, the fusion energy that is caused by the alpha deposition in the plasma. Remember, you need sufficient rho R of about 0.3 of a gram per square centimeter to be able to have significant alpha deposition. So you see NIF is a major new achievement by the program, and I'm looking forward to even more in the future. So how do you look at metrics of progress in ICF? And again, I will now talk about direct drive in a minute. First of all, one metric is the fusion output equal to the energy in the hotspot. Well, that's been done. The typical energy in the hotspot is 7 to 10 kilojoules, and we've been producing much more in fusion. The next metric would be alpha heating dominates, and I think NIF has demonstrated that. The energy released by fusion is 5 times that of the total energy into the capsule. That's a very nice result. The next metric, which which NIF is working on, is to get the energy of fusion equal to the energy in the capsule, which would be about 200 to 300 kilojoules. That I believe that will happen over the next several years. And then, of course, for laser direct drive, it would be about a megajoule. Remember, the fusion device and indirect drive is not the hole room; it's a capsule within the hole room. So capsule gain would be about a megajoule in NIF for direct drive. A target gain for energy, that would be an indirect drive. That would be 5 to 10 because you have to compensate for the hole room losses. And then for laser direct drive, it's about a capsule gain of 1. So getting a few megajoules out of a direct drive capsule would have an energy gain of 1. Now, of course, ignition will be alpha amplification of 20 to 30. And this is something which we are working now over the next decade to demonstrate on NIF and to do the physics on both omega and hopefully on NIF too. Now let's talk about laser direct drive, but it gives you a sense of the project, the metrics and how we improve from small amounts of fusion to reasonable amounts of fusion, ultimately to large amounts of fusion. And the nice thing about ICF, this can be done on a single shot facility, which allows all the complexity of the high rep rate that I talked about not to be built to be able to show you the physics works. All right, now let's talk about laser direct drive. So it's important to recognize that we do direct drive on both NIF and Omega. Omega is configured for direct drive, of course. We do laser and how the light couples, what is the degradation mechanisms in both physics and the laser, and then, of course, hydrodynamic implosions. The typical Omega experiment is about a millimeter, about a millimeter diameter capsule. We put 25 to 30 kilojoules on the target. On NIF, we do experiments to look at how the laser couples. At these bigger plasmas, the targets are about 4 times the size, because as I mentioned, it goes as the cube root of the energy ratio. Of the coupling, we look at mechanisms for degrading implosion, and also we do some implosions. So it's very important to recognize that direct drive is done on 2 facilities in the US, both NIF and Omega. Okay, so how do we look at progress? This has been reported in a lot of papers, and what Omega also has is a very high shot rate. We can do 5 implosions a day, which is high for this field, not high enough for energy. And Omega is a very reproducible facility. And so we were able to do systematic experiments, mine the data to develop predictive modeling tools. And so what this has been developed by Ricardo Betty and his students. We use modern data algorithm techniques, machine learning, to be able to take modeling, computer calculations, and experiments and map them together. This gives us a predictive capability, which I will then demonstrate, and also allows us to look at degradation mechanisms to understand. So here's an example. Here is the yield that we've measured as a function of how long it takes before we shoot the implosions. This is related to helium buildup and radiation damage in the ablator. Here's our model, and here's the data. You see how well it agrees. Another degradation mechanism is the target's not perfectly symmetrically illuminated. What if we have the target not at target chamber center? So the beam's a little bit higher on one side than they are on the other. That creates low mode drive asymmetry. Remember, convergences we want are typically 20 to about 20. And so that obviously impacts how much energy is effectively converted in the implosion. And here's our data, and here's our model. You see how well it agrees. We can also, NIF Omega has 60 beams, and it has a mode of 10. This is a Legendre polynomial, about 10, which can be enhanced by how the light is coupled. And so we can actually do experiments where we look at the laser absorption pattern as a function of these mid modes. And you see here again and we do that by varying the target size, and you see how well it agrees. And then we can do experiments where we look at hydrodynamic stability, and that also is well mapped by experiments. So this is a very good predictive tool. We're continuing to refine it. Do systematic experiments because, again, the world is not ideal. And what we do here is look at what happens as we change the beam quality of the laser. We do this by, and without going into details, but we do this by changing the smoothing requirements, and we look at how much the yield goes as we change the smoothing requirements. And that depends on the quality of the implosion and other things. And you see that we're able to map this pretty well. Here's alpha. If the target is offset, we use 3-dimensional diagnostics, which I won't go into, which tells us how much when you have the target offset, when the target stagnates, not all the kinetic energy of the implosion is converted into pressure. Some of it remains in residual kinetic energy. And that's when typically it can be up to 100 kilometers a second. And of course, that degrades the yield. And you see we're able to map that also. And so learning why the world is not ideal and how to fix it is a key part of the experiments. We're also looking at very detailed physics about what happens in the early phase of the implosion when the light first shines on the target. And remember, the target initially starts off as a dielectric. It's not a plasma. But when the light first hits it, you form a plasma, mostly by multi-photon ionization. We now have this in our codes, and we put this into our physics models to tell us how uniform the laser must be to be able to implode it well. And here's examples of the data at different intensities with this little early part of the pulse. And you see our models, which is the blue, and the data, which is red, shows our ability to measure this. So this is a new thing that we're doing actually in concert with the University of Bordeaux, a lot of work with our European colleagues to understand the physics of details. When you put this all together, you see how well we do. Here's our yield as a function of our prediction. It's a 45-degree line. And this is getting us into very high performing targets that we will scale in a minute. And here also is implosions we've done on Nif, where we've taken basically the blue is the measured performance and the red is our multi-dimensional code, Draco. And you see how well we're doing in predicting the fusion yield, even in implosions on Nif, which I will explain in a minute, are not ideal. So how do you scale a mega to a larger facility? And so it's called hydroscaling. And what we do is basically keep the joules per gram the same. And that means that we keep the velocity of the implosion the same, the quality of implosion the same to get the same pressure. All we're doing basically is using the higher energy to be able to increase the confinement time. And that basically goes again roughly as the third power of the energy. And here's an example of doing hydroscaling on Nif and Omega already. This is a Rayleigh-Taylor experiment. Without going into details, these are the features of a Rayleigh-Taylor instability done on Omega, and then the same experiment done on Nif. And if you go through the details, it shows the growth rates are self-similar and looks very well. So this is what we would get. This is the fusion yield as a function of how big the target would be or the laser energy. So here's what happened. Here's if we would take the best results from Omega, we would produce yields of around 850 kilojoules for an absorbed energy of 1.3 megajoules. Remember, Nif can get 2 megajoules. If we get some of the physics fixed, we could get almost 2 megajoules of absorbed energy. And what that would, and this is about, it turns out that we're about 80% of the requirement of this p-tau for ignition. So good progress has been made over the past number of years, and what we're doing over the next number of years in the future is to get this as close to 1 as we can. Here's an example of what an Omega implosion looks like. Here's it scaled with Nif, and these are just showing how close we are to getting megajoule yields out of an Omega scaled Nif, or Nif scale, Omega that would be scaled to Nif size. But of course, Omega Nif is not set up for direct drive today. It is set up for polar drive. So here's the Nif Target Chamber. Here's beams coming in from the top and bottom to be injected into a whole room. So we have a program called Polar Drive where we actually take the whole room out and we irradiate the target with this non-uniform beams. The advantages of Polar Drive, of course, and this will be talked about a little bit later with Mike Tobin, it gives you some reactor flexibility that you don't have to have 4 pi illumination of the target. And that's a good thing. It also allows you to put B fields and other things in the capsule to do interesting confinement. And actually, of course, most importantly, it reduces the impact on Nif. Nif has ports, as you see here, for symmetric illumination, but they're not yet filled. And of course, you have 4 pi diagnostic access. What we would do, of course, is also change how the spatial uniformity of the beams are done on Nif, which I won't talk to, but that's we'll talk about that a bit later, but with putting different phase plates on. We're working now with Livermore, General Atomics, Los Alamos, to come up with a plan to be able to do this on Nif with the quality that's needed. Now, we have also done Polar Drive on Omega. Omega is not ideal for this because it was set up for symmetric illumination. But what we can do, actually, here you see over on the right what an Omega target looks like. You can actually tailor the target by putting right here where the beams are coming and grazing instance, you can thin the target up here so there's less absorption. So the velocity is the same. Here the absorption will be higher, so it'll be a little bit thicker. And so by shimming the target, we actually can get nearly one-dimensional performance. This is an example of how you shim the target as a function of angle here. You see that goes from 28 down to a couple microns. That's all it's needed. We do this, we can get the yield close to symmetric illumination and the areal density, what we would have with symmetric illumination. So we believe that we can do Polar Drive on Nif eventually with high performance. And that's part of the program we're doing. But what Nif allows us to do today is to study the physics of megajoule lasers and particularly how the light couples into the plasma. Here's an example of how big a plasma would be on an ignition scale Nif. To target the corona surrounding the capsule would be 600 microns or size. We're doing experiments on Omega on Nif, which is bigger than that. You see on Nif right now, we're doing implosions of about half that. And you see Omega being about 1/4 the size in terms of cube root of that. It's about 1/4 of the dimensions. Temperatures, you see this and then of course the intensity. So what we're able to do is to do the physics of the plasma coupling with NIF on its present configuration. One of the problems is not only the broad geometry, but the quality of the beams on NIF are very poor. And so that impacts our ability to understand the coupling physics. It makes it a worst case scenario. So good coupling on NIF today means much better coupling on NIF when we make modifications for direct drive. And here's the type of experiments we're doing. Here's a capsule or a solid sphere that we're illuminating with a NIF. We watch the shock waves. Right? We watch the shock waves propagate in. It tells us how much energy is coupled without the complications of implosion. And here's what you see as the radius of the shock as a function of time, and our measurement and our calculations, very well coupled. And this gives an absorption, to give you a sense, about 80%. We also can change the capsule by shimming it. This is an X-ray radiograph of a capsule that is spherical. Here's one when we make it a little bit thinner on this side, and you see in the X-ray when it's imploded, we've reduced the asymmetry by about a factor of 5 if you do the details. So we can make a non-uniform implosion uniform by fooling around with the capsule. We also can study the generation of high energy electrons, which I'm going to talk about in a minute, on these large scale plasmas. We look at the different processes and understand not only how hot electrons are made, but where they go. This is what a target looks like after it's been illuminated. This is a dense shell, which is imploding. This is a plasma surrounding it, where the energy is coupled into the plasma. And we've been doing experiments to show us how much energy goes here of these hot electrons. And it actually is very encouraging. It's about what there are acceptable levels for doing high quality implosions. Now let's talk about innovation. What's the future going to be? And this goes back to, this is a conversation which is true. I've talked to all the people here. This is John Nuckells, the father of ICF, at least the US. Edward Teller, who you all know. Marshall Rosenbluth, wonderful plasma physicist, and John Hunt, laser designer. When lasers were first demonstrated in 1960, John Nuckells said, we can do fusion without having to explode a nuclear weapon. And Teller said, not if plasma physics gets in the way. Marshall said, you should be worried. And John Hunt, I drew this cartoon in 1978, and we had already had plasma physics issues, and the solution was short wavelength alcohol or short wavelength lasers. So of course, let's talk about lasers. So here's Albert again saying simulated emission is a lot more useful than I ever thought it would be, and a lot more useful than people thought when it was demonstrated in 1960. So first, let's talk about what the problem is. So here's a laser. So on the left, we have a laser beam propagating into a plasma. The electrons, of course, being very light, oscillate in the field. And you all know that an oscillating or accelerating charge radiates. So it radiates electromagnetic wave. That wave beats with the incoming wave with a ponderative force, makes a ponderative force and puts the electrons where the troughs of the wave. If the wavelength of this trough is matched to an electrostatic mode in the plasma, you have instability growth, and the energy will be converted into these plasma waves. Now, that's with a single beam. Today is you have not growing from noise, you have multiple beams, because every laser experiment implosion has multiple beam illumination at the same place in the plasma. So instead of growing from noise, second beam, if you will, is already at large amplitude. And this can cause instability problems. I'll talk about that. Here's an example of a thing called CBET, which is Brolon scattering. Here's a laser beam coming in, another laser beam coming in. They drive together an ion acoustic wave, which basically forms a gradient in the plasma and can move the energy exchange energy between these two beams. So this is a problem in today's laser experiments. So if you look at history, and I like history, and I've been in this program so long, I can tell all the history. This is how lasers have evolved over the past 40 years. When ICF was first started in the 1970s, the two high-powered lasers were CO2 and neodymium glass. They could generate the powers and intensities you needed for implosions. Unfortunately, we found out that plasma physics got in the way because of what I just showed. So second generation lasers were converting these into the high harmonic, the 3 omega, and the ultraviolet, because these instabilities go as the intensity times the wavelength squared, make the wavelength shorter, the threshold of the intensities goes up. And of course, that saved the program. So second generations were converting the light into the third harmonic. But one of the things also to remember is that this is a laser beam here. Our target, a diffraction limited beam at a 1/3 micron with, say, an F10 optic is a few microns, and the targets are millimeters. And so what we do is we irradiate the targets in the intermediate field and look at all the structure in the laser beam. The beams are too spatially coherent. So what happened, Rochester, NRL, and Osaka invented techniques to destroy the spatial coherence with phase plates and the like. And so we took this spatial frequency, made it in a controlled high spatial frequency. And then actually we added a little bit of bandwidth to move it around. And this is what a modern laser looks like. And this is what Omega does. And what we're talking about now is taking these lasers, which have bandwidths of about a few tenths of a percent, so they're still temporally coherent, and now making them broad bandwidth. And that means they will be temporally incoherent and be unable to drive these plasma instabilities. So these are 4th generation lasers. This is the innovation we're doing now at the University of Rochester. So laser technology developed for short pulse lasers has enabled this to happen. So broadband laser was developed for ultra high intensity lasers because the shorter the pulse, the higher the bandwidth I need. And technologies to develop high bandwidth optical parametric amplifiers invented in Europe generate the bandwidth that can now be used to make ultra high intensity lasers, very short pulses, or broadband temporally incoherent long pulse lasers for ICF. We call this laser we're developing Flux. It's a 4th generation laser. Without going into the details, KDP is again critical. We take a broadband light signal, we put that and we interact with a crystal with a narrowband green pump. That green pump transfers its energy with the crystal into the broadband signal and makes broadband signal actually another broadband pulse called the idler, and a little bit left over. This generates ultra broadband that we use together. And what this happened, this is an example, this is down here, we've been able to make on a small scale 13 terahertz bandwidth, which is a factor of more than 20 higher than we have right now on Omega. You can do this with pulse shaping. Here's a nice pulse shape here. And what this does, it gets rid of the plasma physics. So first of all, it increases absorption from about 50 to 90%, and also reduces this laser imprint. This is a smoothing rate of the laser beam on Omega. You see that it smooths in about 50 to 100 picoseconds, and it's a function of bandwidth. With a high bandwidth laser, the smoothing time is less than a picosecond. So imprint will go away. We use modern computer codes to tell us what we need to do. So here's what happens as a function of bandwidth. Here's the laser absorption. You see on Omega, we're getting about 55, 60%. If we got rid of CBET, we get about 90%. And remember, the pressure for ignition goes as 1/2 of the energy in the hotspot, the square root. So if we increase the absorbed energy, the pressure we need for ignition goes down significantly. So also the pressure that implodes the capsule also goes up to the 2/3 power of the absorbed energy. So as we increase the absorbed intensity, you worry about instabilities by hot electrons that make these bad things. Well, it turns out that a little bit of bandwidth, I can raise this threshold by 3 or 4 times, which will allow me to implode things at intensities of 10 to the 15th. And here I shows I can get rid of hot electrons with bandwidth of about 1 or 2%. And we're operating right now, we have demonstrated laser bandwidth around here. What we're going to be doing is actually taking a broadband laser and showing what its physics can do using Omega as a plasma source. We've already done this on a smaller bandwidth system using EP. As Manolo said, EP is a short pulse laser, which means it has a reasonable amount of bandwidth. It's a picosecond or so we can get bandwidth, which allows us to do tuning. So here's the gain curve of EP, and we can tune over this frequency range here to see the effect of tuning lasers on instabilities. And we can actually use the other beams of Omega to form a plasma that can control the temperature and density and diagnose it. Here's an example of an experiment. We form a plasma with beams of Omega. We shine one beam in from one of the other Omega beams we don't use. Here's our tunable laser. Here's a plasma waves generated. We can see what happens with the physics. We can do this with a single beam, can interact with multiple beams in the backscattering geometry. So the scattered light goes out this way, or the energy exchange, or we do it in the forward direction where we see the energy exchanges in the forward area. So we've done those experiments. Let me just show you how that looks. Here's a simple demonstration. Here's a pump. Here's a seed beam. Here's a pump beam. Again, we've made the plasma. So here's our seed. This is a time history. And here's our pump. And when our seed beam is higher frequency than the pump, what happens is it gives energy to this beam. So energy exchange takes place. So you see how this energy goes down. When we make it a little bit less frequency, it takes energy from this pump beam. You see why this is important, because it moves the beam energy around in ways that you don't want, and you like to know where the energy is deposited, so you want to get rid of this process. And so this is a way of showing how it works. We've been able to do this, take this results and do the same experiments on Nif, and by tuning the lasers on Nif, we can actually change the symmetry and the absorption and show the CBIT can be controlled. So this is a major research success over the past years. And we're going to do the same thing with flux. Right? Let me go back here again. We're going to take this broadband laser, shoot it into a mega, and we're going to study the physics of broadband light in plasmas. We'll do it with lots of different frequency formats. And our hope is that the next laser, one of the next lasers built, will have this capability of having temporal incoherence. But let's not just think about that. You're going to hear a talk later on by Connor Galloway and reactor implications by Mike Tobin. What if I used a different laser than a solid state laser? A gas laser has a lot of attractive features. Gas is a lot cheaper than glass. It also has does not have a lot of the nonlinear effects, the N2 effects that happen in solid state media. But the challenge with getting a gas laser is that the energy storage time is very short. And so when I pump this, the laser beam is on as long as the pump power is on. And typically these lasers are pumped with pulse power. So typically they're microsecond long. We know ICF wants nanosecond long. And so I can do this by actually, and you'll hear about this from Connor. There are ways of compressing the light using a gas media, whether it's called Brillouin compression or Raman compression. It happens in plasmas too. And where I can take a long pulse beam generated in this pulse power amplifier and have a short pulse beam that comes in and it robs the energy from the long pulse beam and can give me an enormous amount of energy at a relatively low cost. And this is a very exciting and innovative new innovation. So I can get lasers down to $10 a joule, 10, 20 bucks a joule. I can make not megajoule lasers, I can make tens of megajoule lasers. And you hear about that later on today. All right, now let's talk about some innovation in targets and design. So first of all, remember I told you we need to be able to make thousands to millions of targets a day. Well, additive manufacturing is going to do it. We're going to start printing targets in the future. We're actually doing that now. Here's an example of a target that's been printed, and we actually put a low density foam outside of it as a feature to reduce imprint. I won't go into details of this, but this is a target that has been printed. We're actually learning to do very advanced diagnostics to look at imperfections in the target, and we can shim it. As I mentioned before, very important. This is the ice layer, and you see up here it's 190 microns, and down here it's 140 microns. We can control the very spatial non-uniformity of a driver by putting spatially non-uniform targets to match it with the DTI. So lots of innovation there. We're also innovating targets. This is a direct drive target that actually is made out of liquid DT and a wetted foam. And here the laser pulse is used to generate an imploding shell. So instead of having a target, which is a shell of DT, we make the shell of DT by the pulse duration of the laser. And we call this an imploding shell. These targets will be very cheap to fabricate. We'll be doing experiments on the Mega next year to test this concept out by Valery Gontarov. It's been talked about in physical review letters. Now, I want to just talk about energy. This goes back to the Innovin design. Multi-megajoule lasers would enable me to implode milligrams of DT. Remember, I told you to get 100 megajoules of yield, we need less than a milligram. The more energy I have in the laser, the more mass I can implode. And that means the more mass I can implode, the less convergence I need to get the rho R, because for a given rho R, the density that I must achieve is inversely proportional to the square root of the mass. More mass means less density to get the same rho R I need for burnup. And this shows you an example of what the peak density I need is a function of the DT mass. And you can see if I can get DT mass in the 20 to 30 milligrams, I don't nearly have to achieve these 1,000 grams per cc of DT to get high burnups. I can do less than 200, about 100 grams per cc. Much easier implosion to do, much less convergence, much less susceptible to hydrodynamic instabilities. So this is a very important initiative that we will continue to look at carefully. And Connor Galloway will talk about the laser. Mike Tobin will talk about an interesting target design. So as I mentioned, ICF comes in different flavors. Here we can do something which is a hybrid using both X-rays and direct drive. We use the X-rays basically in this target, and I won't go into all the details here. We use a first pulse laser to make X-rays that create a plasma atmosphere that surrounds the capsule, begins to implode. Then we hit it with a direct drive. We directly illuminate the target with the laser. This can be done with just two-sided illumination. And because of the details of the design, you can get symmetry that allows you to get the convergences that you need, which again are much less because of the high mass that you're imploding. We'll be doing we're looking at doing experiments on Omega to test out this concept. And Mike Tobin will tell you some of the reactor implications of this, which are very beneficial. I'm going to finally end up with a few spin-offs, why I got involved in this field and why it has value in addition to the fusion research. So you all know that microelectronics dominate the world. Not only does the world need power, it needs microelectronics. And the way in which it's done right now, the most advanced microelectronics were invented in a process called extreme ultraviolet lithography, which was invented by the ICF program. In many ways, it's a miniature IFE target process. What you do is you shine a laser, you inject 10 targets. Right now they're 10. That laser makes about 100-volt X-rays. Those X-rays are captured by a mirror, thrown to an imaging system, and printing a circuit. So what this is done at 50 kilohertz, much more rep rate than an IFE chamber would be, but the basic concept is the same: pulse lasers, injected targets, and process. So this was first demonstrated in the late 1980s at Livermore, Sandia, and Berkeley. This is the first stepper. These are called steppers because they illuminate and then the wafer steps, and they're called steppers. Here's a system now, which is commercially available. It's made by ASML in Europe, even though this was invented in the US and Japan also, but now it's by this company. And so if you buy a new iPhone, an iPhone 12, it's got about 8 billion transistors in it. And the critical dimension is 7 nanometers, 70 angstroms. So this is all enabled by fusion research. Remarkable thing. Generates, it's let's just say validated all fusion ICF for a long time. And now, of course, another thing that happens in what's done is the science program. We make matter in extreme conditions. And of course, most of the universe is in extreme conditions. So we study planets, we study stellar physics, we study astrophysics, magnetization of the universe by doing laboratory experiments. So we complement observational astronomy with laboratory experiments. And this was all enabled by the physics and the technology and the drivers developed by ICF, a very active program. We have it at Rochester, around the world. Nature papers appear frequently on this. One of the things that's also recently happened, we have been able to demonstrate by compressing hydrogen, sulfur, and carbon to high densities, we can make superconductivity at room temperature, 14.4 degrees centigrade. This is a picture from the movie Avatar, which if you all saw the movie, one of the themes was, how do I get this material, which was called unobtainium. And we've been able to make superconducting at room temperatures. Now, of course, it's at 3 million atmospheres. We think we know ways of getting this down to ambient conditions. All this came out of fusion research. And of course, high peak power lasers. The Nobel Prize in 2018, done by Gerard and Donna Strickland. When Gerard was at Rochester, Donna was doing her thesis here. Got the Nobel Prize in 2018. And we all know what high peak power lasers have done, the ELI program in Europe, all the work done in Japan and China, and also the US. And of course, this has led to the development of high energy pulse lasers and high average power lasers. One of the futures will be, in addition to the laser that I talked about with Innovin, an IFE solid state laser would be diode pumped. So laser diodes are being developed for multiple applications, and you can get lasers now with average power of hundreds of kilowatts. This is being done for national security reasons with wall plug efficiencies that are greater than 30%. NIF is about 0.5% efficient. Omega is about 0.1% efficient. This is 30% efficient. So what are the applications? Of course, IFE, extreme physics, laser accelerators, we all know about that. A lot of industrial processing that's being generated by having these lasers, and of course, other national security things. Let me end with my last view graph. As one of our famous presidents would say, Teddy Roosevelt, an interesting guy in many ways, but he was great with quotes. Far better is to dare many mighty things, to win glorious triumphs, even though shackled by failure. Believe me, I've had mine. Than to rank with those poor spirits who don't try. So my words to all of you students, and of course those interested in the field, fusion is a worthwhile endeavor. It is a career worth spending time on. And as I like to tell people, as long as we've been working on fusion, when we finally achieve it and make energy for the sake of the planet, it will be those who started it and those who finish it will be on the podium getting the medal, just like in every other relay race that comes on. So that's my talk, and I hope you enjoyed it, and I'm now done. Any questions if we have time?
Well, thank you very much, Mike. Please, we give you all the thanks. And
so if there's any questions, I'd be glad to try and answer them.
Here you can show that your presentation, even that it was not completely well seen, but was really very, very, very important, really very interesting. Mike, it was a great presentation where I want to advise all of you. Mike presented not only the past, but the present and, which is even more important, the future. So remind this presentation because it's really great. I want to advise all of you that you will have, if you agree, Mike, if you agree, we could share your presentation with the students.
Absolutely.
Yes,
it's yours, whatever you want.
Thank you very much. So now is the moment for the questions. There is any question about the progress of ICF, IFE, from some of you? No? Let's see if our colleague did some question. No, we have no questions. Okay, so if not, oh yeah, okay. Dimitri has one question for you.
Hi, Mike. Can you say a word about the fast ignition and shock ignition programs at Rochester?
So fast ignition, shock ignition are interesting concepts which have been around since the late 1990s and ongoing. The advantage of those, of course, is that you separate the ignition from compression. So you send a driver, obviously, to compress the target to high densities, and then you then light the match by a different laser. So work in the U.S. is still not focused on that. Most of it is, again, focused on, say, the traditional ways I discussed. But we have done experiments on Omega, basically trying to understand the coupling of the intense light, because to do shock ignition requires intensities in excess of 10 to the 15. And so one of the challenges is to understand what does the coupling take place when you're exceeding the threshold for various instabilities I mentioned, either Raman or Roland, which reduces absorption. So we've done experiments on that, and to see how much energy is coupled into how much energy is effectively used, and that looks attractive. We have not done experiments on so that's been what the focus has been, looking at the coupling of the shock-induced pulse. We have not done fast ignition work for a long time. There is some growing interest again in proton fast ignition, where high energy protons, which are generated in the short pulse laser interactions, by several different mechanisms, are used as the igniting pulse. So we have done experiments to begin to look at the efficiency of generating those protons, how different ways of target configuration, contrast variation with the laser pulse. So the work so far has been looking primarily at if you will, the ignited part of this. We will probably be doing experiments over the next several years looking at what's a compression phase look like, where we tailor the laser pulse just to try and assemble a high density compressed target, where we don't worry about the hot spot. It's just the compressed target. We'll probably be doing that. These dynamic shell targets have some features of that, which as we try and understand making the dynamic shell, we'll try and see if we can get a dense target to start with without that. So it's not the main line. I'm hoping that we can, I know the shock ignition, and both of these are of interest in around the world, and my hope is that we can develop more collaborative programs with our colleagues, in Asia and Europe to do some integrated experiments at the right time.
Okay, thank you, Mike. I have a question. Actually, you teach clearly to all of us that in inertial fusion, we have separated driver, laser, we have the target fabrication, we have a chamber. In your opinion, which is the strategy, which will be your strategy for research in these three areas? So my question is, we need to progress first in laser target implosion at the same time that we progress with chamber, or the strategy from the point of view of time, the schedule need to be different in the three areas?
Yes, so I mean, to me, this, the strategy is pretty clear to me. First, really showing to demonstrate that you can assemble a high density core, if you will, and actually understand the sensitivity to hydrodynamic instabilities. By not having to form a hotspot, the hydrodynamics will be, I'll say, more favorable. We don't need to have this hot, hot central region, which, remember, hydrodynamic instabilities occur twice in an ICF implosion. During the acceleration phase, with the noise sources that are both target imperfections and for direct drive, the imprint, and then the deceleration phase when the low density hotspot is decelerating this cold shell. So by not having to have that process underway, be interesting to see how well we can assemble these, if you will, these cold cores, and how much it relieves the target fabrication and other, if you will, issues that are concerned. So the first thing is to do that. And I think we will do that as part of a program that's based on the, as I mentioned, dynamic shell. And I think any collaborative activities, Omega is the best facility for doing that in direct drive. And so that's something which I would hope that we would develop collaborations with our European and Asian partners in that, because of using the quality of Omega to do that. Of course, the other one is to continue to develop efficient electron and ion source generation and understanding how they stop in these plasmas. So the strategy will be basically, I think I'm trying to answer your question, it will go along those lines. First one will be, and I'm very actually anxious to try and assemble these dense targets, because also it's interesting for equation of state. We do equation of state by doing planar experiments where we shock or basically tailor it so that the entropy is small. But compression allows you to get to higher pressures, and so this will be a natural thing to do with the equation of state studies that we will do. So I think that's something which will be a growing focus over the next several years here at Rochester, which of course will directly go into these two-step processes.
Okay, Mike, I have one last question from our good friend, Professor Kunio Mima from ILE Osaka. His question is, which play roles of the machine learning, that means artificial intelligence technology, play for the target design of IFE? You mentioned something about machine learning.
Professor Mima, I have a good cartoon with him, by the way, which I should have included. But no, I think it's very important. We're using a very crude version of this now with Omega. The ICF field in general is data starved. So we are limited in how well we can use these modern techniques, machine learning and such, to be able to design targets. And of course, that's something which is very, very important for IFE, and actually very important for ICF in general. So what our view of what a future Omega would be, what do we do? Omega is now many years old. We're starting to plan for what would Omega be in the next decade. This decade, we need to do research on the next generation laser. So one of the things we're thinking about for Omega in say 6, 7, 8 years from now is an Omega that fires every few minutes. So instead of doing 5 implosions in a day, you do 100 to 200 implosions in a day. And that will enable you to be able to really take advantage of these modern machine learning and advanced algorithms in doing that. You'll have data to compare against. And without data, machine learning to me is, again, not enough. You must be able to combine machine learning with a lot of data to be able to teach both the algorithms and to teach the hydrocodes what's important. Again, we're doing this in a crude way right now, but if we could do hundreds of experiments a day, that also means we have to have target fabrication that can provide hundreds of targets per day. So over this decade, we are working to be able to put the story together to be able to do both of those things. But I think that's what the community needs. Doing experiments at Hertz rep rates right now with complicated targets is a little bit too complicated for us. But doing experiments every few minutes, with a full suite of diagnostics and the fuel capability is something which I think we do know how to do, and I think we can find a way of doing that in the next 5 or 6 years. But I agree with Kanoki. It's very, very important to use these modern tools to design targets, and we're doing it right now, as best we can with the limited data rate we have from Omega.
Okay, thank you very much, Mike. Oh, wow, Dimitri has just one last.
You were mentioning krypton fluoride. So what is your personal feeling? I mean, the future will be more like a gas laser or like a solid state diode pumped laser?
What type of laser do I think for the future?
The future will be more like a krypton fluoride gas laser or like a solid state diode pumped laser?
So it's a very good question, and one which I think it's premature to answer. One of the advantages of a solid state laser is that there's a large infrastructure in this already, and the development of laser diodes, which is absolutely an enabling technology for the future, and that is being driven by other applications in fusion. You can get laser diodes now which are 65% wall plug efficiency. So that means 100 watts of electrical power comes in 65 watts of optical power. Then I can couple that into a solid state medium. So getting efficiencies at the fundamental of 40% are very, very possible, and I expect that to happen. And I have seen lasers that for national security which approach those efficiencies. Now, of course, that's at the 1 micron, so you have to tailor the laser to be able to do what is necessary for target physics. It must be able to do it at a higher frequency, of course, must pulse shape it and the like. So having efficiencies in the end, which are, in the 20 to 30% electrical efficiency is a possibility with solid state, even with this. And there's some ideas like a thing called star driver, which maybe you can even have things close to 40% efficiency. The challenge, of course, is getting energy, because the cost of a solid state laser is you're using a gain media, which is expensive. And also you have other nonlinear effects which limit what you can do. One of our challenges with the flux is what happens in the propagation of this temporally incoherent broadband pulse through the amplifier chain. So that's something which we are also addressing in the flux project. But the advantage is, we have a lot of infrastructure, a lot of experience, and I think pathways to high efficiency. The advantage of KRF, and NRL in the US is looking at argon fluoride too, which is even a shorter wavelength, that's 1900 angstroms. The advantage of an excimer laser, of course, it's a gas. Gases are cheap. And that makes a big, and of course, nonlinear effects are much reduced. The challenge, and then that allows you in principle to get to high energies, because there are techniques of making this pulse power laser, and excimer lasers are pulse power lasers, to be able to get them at the pulse widths that are necessary for ICF, which are in the nanosecond regime. So there are pulse compression techniques, and you're going to hear about that from Connor. And this again has been looked at for many years, but not a whole lot of effort. Livermore, once the 1 micron coupling problem was clear at Livermore and Holrooms, there was work being done on pulse compressing krypton fluoride. But when it was clear that you could make large KDP crystals, that effort stopped. But NRL has done some nice work on this, and they use a technique called optical multiplexing, which is another way of what you use. You have the amplifier on for a long time, you put a short pulse laser through it, and you put it through the amplifier many times, and then combine it at the end. That's called optical multiplexing. It's more complicated than optical systems than what Connor's going to talk about. So the advantage of a gas laser is it could be cheap, and that means it could be high energy. And that, as you will see, has a lot of advantages of reducing the complexity of implosion. The other challenge though, is that the efficiency of these systems will not be as high as a solid-state diode pump laser. They will be in, let me be optimistic, a 10% range is the best you will probably be able to do. And so that means to get an IFE system, you need higher gain targets. Because you need a product of the driver efficiency times the target gain of order 10. So a 10% efficient driver means I need a target gain of about 100. A 30% efficient driver means I need a target gain of around 30. And so it puts more demands on getting high performance implosions. But again, the ability to do more massive implosions sort of compensates for that. So at this stage, it's too early for I think to make that decision. We're focusing on solid state here because that's where we have the expertise. But we're monitoring the work that will be done with excimer lasers, both in the private sector and around the world. And then eventually we'll have to decide. But right now, what we want to do is continue to derive the physics that makes the case strong for an IFE plant in the future. So I know it's a long answer to your question, but there's the pluses and minuses on both. You see, it's not so clear at this stage which one to select, but there are pluses and minuses for both.
Okay, Mike, thank you very much. Before say to goodbye and many thanks, I want to let know the students that when they have the presentation in their hands, they will see the cartoons. The cartoons are made all from Mike, and be sure, all of them are fully realistic. So, teller is teller, knuckles is knuckles, hand is hand, and Rosenblut is Rosenblut. So, thank you very much, Mike. Thank you very much. We applaud you very much for your presentation. And bye-bye.